Before we get into the specifics of how to set our transient response and improve our steady state error, let's briefly talk about the different ways we can implement these compensators. And so what we're going to see is that there are two basic configurations. Due to limited time at the time of recording this video, we're only going to look at this first one, which is our cascade compensation, but there is also a second type as well that's worth mentioning. So in this cascade compensation, we have three blocks in our forward path. So over here, our G3 on the far right is going to be our plant or the process that we're controlling. Our G2 is our original controller. So this is from our uncompensated system. And then this G1 is going to be our cascade compensator. And so what we notice is that, as I had mentioned in the previous video, typically this compensation is going to occur on the low power side of the system or before we get to that plant or process that we're controlling. So pretty simple configuration. The second one is going to be feedback compensation. So for 2, we have feedback compensation. So this is the one that we're not going to have time to get to. Again, at least at the time of recording this video, it might be that we come back at a later time and add a video or videos related to this method as well. But of course, for this semester at least, you can read more on that in the textbook if you're interested or if it's relevant to your job or whatever project you're working on. So our G2 of S is now going to be our plant. So again, this is the furthest right system in the forward path. Our G1 is our original controller. And now our compensator is in our feedback loop. So here we have our feedback compensator. And so when you choose to use one or the other depends on the exact system and the exact needs of the problem. But we do have a couple options, and that's worth knowing at least, even if we're only going to spend a lot of time looking at this first method of cascade compensation. So one other note we want to talk about with our compensators is we have ideal versus non-ideal compensators, and there are going to be benefits and drawbacks to using each one. So ideal versus non-ideal. Compensators. So first let's talk about our ideal compensators. So our ideal compensators. And so what we're going to see with these ideal compensators is that we're going to be able to have pure integration and pure differentiation. And so remember, we talked about just briefly in the previous video that for improving our steady state error and improving our, or not improving, but getting a desired transient response, we're going to have to be adding integration and differentiation. So with these ideal compensators, we can have pure integration and pure differentiation. And what we're going to see is that, at least for pure integration, we know from our unit on steady state error that this means that we can completely reduce, or not reduce, we can completely eliminate our steady state error. There are some drawbacks, of course, to this. So in order to implement this, we're going to need active components. So to implement, we need so-called active components. And so what do I mean by active components? So we've kind of glossed over this in earlier units as well, but typically when we talk about active components here, you need to be thinking about op amps or operational amplifiers. And so for the mechanical engineers, if that doesn't make sense, don't worry about it. Electrical engineers, you should be familiar with op amps. And what we know about this is, compared to what we're going to look at in a little bit, this can be a little bit more expensive. So not terribly so, and it depends on how many of these we need and what the quality is, and of course there are all kinds of specifications related just to that. But in general, compared to the option that we're going to look at here in a second, it's going to be more expensive. So we would say then the benefit of using this ideal compensator is that we can drive that steady state error to 0. However, doing that is going to be more expensive. So as always, we have these sort of design trade-offs. So the second option then is, of course, our non-ideal. So we have these non-ideal compensators. And so instead of having these active components, we're going to see that these consist of only passive components. So only passive components. And so what the result is going to be is that we're going to have some non-zero steady state error, because without having a pure integration, we can't drive that steady state error to zero. However, because we're using these passive components, that means our system is going to be cheaper compared to using active components. And so what do I mean by passive components? So these are, of course, our resistors, our capacitors, our inductors. And so typically those items are going to be cheaper than our op amps. So here we would say that an advantage of this non-ideal compensator is that it's going to be cheaper to implement. However, the drawback or con of using these non-ideal amps is that we can't drive that steady state error to zero, and we in general just don't have as much accuracy. So again, because of our limited time, we're not going to spend any time talking about the components behind these compensators. They're also, at least in the textbook, we're focused more on electrical networks. So, that's not something that everybody in the class has the same background with. But for those of you who are interested, I would encourage you to look at section 9.6, which has some details on what these compensator networks physically look like. So how are they actually constructed using these circuit elements? And so that's on page 404 in the 8th edition textbook. And so again, this is just giving circuit examples of each of those types of compensators. So circuit for those compensating networks.